Hello everyone, and thank you for attending. So, as we just said, I am about to talk about Coriolis, which is an almost automated tool chain to produce GDS2 from RTL. So, first, I will start by a short introduction about why we do that. What are the reasons behind the creation of Coriolis and Alliance. I will then make a short introduction about what is it to make ASICs and present the design flow. Finally, I will make a short recapitulation of what we did and terminate by a 5 minutes demonstration of what you can achieve with Coriolis. So, the first thing is that I think that we live dangerously, in the sense that the ASIC industry is not a straight pillar, but more an inverted pyramid. In the sense, I talk in the sense of the number of people involved. You have tons of software designers. You have one order of magnitude less ASIC designers, and even less EDA tools. The number of EDA tools actually is maybe 4. You have 4 commercial EDA tools. That is to note. And even less foundries, I mean commercial companies. You may have a little bit more plants, but even the plants are gigantic factories, but they are very, very few. So if a problem impacts one factory, you suddenly have a big problem. And the same goes with the EDA tools. Imagine that one commercial EDA tools fail for whatever reason, and then you may have very bad problems. So we wanted to change that situation. And there are 2 blockages, two roadblocks that prevent us to do that. The first is the EDA tools. At the level of the EDA tools, the problem is the price. If you take commercial EDA tools, the license fees per year is above the $1 million. It's really, really expensive. It makes sense if your design is very expensive also. For example, if you target 22 nanometers or below, then the cost of making the ASIC anyway are high, so you do not have problems paying high license fees. But for older nodes, which are amortized, and into which the cost is maybe, I don't know, it's in the order of 10,000 euros or $10,000, it's $1 million license fee is not interesting. So you cannot use it. For the foundries, the problem is slightly different. The problem is secrecy. Because the foundries, the information that the foundries need to release for you to make an ASIC give hints about the technology they are using. So if they do so, they give very useful information to their competitors. So it's also understandable that they close that information. They don't want that information to be spread everywhere. So that also makes sense when you have a bleeding edge technology, which nobody has replicated yet, but for older nodes, which are commonplace, that makes no sense. You don't protect 180 technology node, because I think I wouldn't say everyone has it, but it's no more a technological challenge, and everybody have it. So in our part is to provide free EDA tools. Another reason to do so is the long tail of technology. This curve shows the number of design, not the number of chips made, but the number of different kind of design started by year and by technology. And what you can see, at least on those curves, is that whenever a technology got mature or a little bit old, then it doesn't cease to exist. Design continue to be made with them. So it's the case, for example, you see I think the 180, for example, this curve, you see that even now there are a lot of design made with it. Even the 180, which has peaked in the years just after the 2000, there are still a lot of design made with it. So tools for all the technology, which are mature nodes, are still very useful. And so now, in order to develop our tools, we need a specific set of competencies. So the first one, obviously, is ASIC designer. When you want to make an EDA tools, you obviously need to know what an ASIC is. So you at least a basic understanding. Then, in order to solve the problem of EDA tooling, you need to understand algorithmics. You need to have a toolbox of algorithm that you understand, and maybe some that you may build on your own. So it's important to master some basics of algorithmics. And lastly, you need, of course, skills in software engineering, because implementing the algorithm needs a lot of skills in software engineering. And as there are a lot of algorithms involved and imbricated, you need to be able to manage big software projects. So this is why, this is one reason why there are so few of people making EDA tools, because you need those 3 specific skill sets, and it's not very common. Even the companies are having difficulties hiring skilled people trained in that specific area. And lastly, to really make a tool, you need time. Those tools are big and complex, and you need a constant involvement under a long period of time. So that's another problem that we are facing developing our tools. So finally, I come to our goals in making Coriolis. So obviously, we wanted first a platform for academics, so they be allowed to develop their own software and make their own experiment without being hindered by commercial tools. I have seen a practical case of people developing upon commercial software a lot of nice experiments, and then the commercial provider just close off the feature or suppressed it without backward compatibility, and all their work was lost. This is really sad, but it did happen. I did see it happen. We also want to make algorithmic experimentation. We want also to build up a community. I think it's the point of this conference, to build a community. How to build a community, of course, is to be public. And not only the tool, but the ability to publish your work. And of course, to share the design to the layout. You will see that we have some possibility there. So also, as I said, there was the money barrier, and we wanted to suppress it so that not only enthusiasts and amateurs can do design, but also small businesses. So it's important for them. So another problem that arises with closed software is that you cannot check carefully your design. You have to trust what's come back from the foundry. You send your chip to the foundry, and you hope that the chip is good and it has not been tampered with. So with the ability to check your design with free tools and to have free design, you can check them. It is starting to be an issue more and more. Next, we have some funny stories about people using obsoleted software, obsoleted hardware, and they needed to have more of it. For example, the NASA did look desperately for ASIC processor for its space shuttle. The space shuttle was designed in the 70s with hardware existing at that time. So in the year the 2000, the ASIC was no longer fabricated. So they need to scavenge on eBay for those kind of processor to just maintain the space shuttle. And this is also a problem for nuclear power plant, for example. A nuclear power plant has a lifetime of maybe 50 or 60 years, and it has been qualified with a certain hardware, and you want that hardware to be available for all its lifespan. So either you stockpile your hardware at the start of the construction of the building of the power plant, or you must be able to replicate your hardware exactly as it was using free tools. Because otherwise, if you trust companies do not produce the same products for 50 years, especially in the ASIC industry. So the first target of Coriolis is mature nodes. We don't want yet to be able to run on below 180 or 130 nanometers. This is well enough, but in the future we will try it. So, as I said, the layout is a big problem, and the right side is the real layout, which is in their NDA most of the time. Notable exception is for Skywater 130 is not in their NDA, so you can access that, but most of the time you don't have access to the right side. So in the late 80s, the Mead and Conway, I don't remember which American university they were, but developed the Symbolic technology. And it was based on a simple observation that was that between technological nodes, what you have is basically a shrink. You have the same dimension, but shrinked. What we do with Alliance, we just added a little more flexibility to that simple shrink, which is delta W and delta extension to add an extension on the delta on the width to give more flexibility. So it has worked well until the 180 nanometers, because at that point, the shrink rate of the various layers did change, and did not change at the same rate. The transistor was not shrinking as fast as the metal layer, so it caused a problem. But still, the Symbolic technology is very useful, can be very useful. It has also another advantage that was not foreseen. The first advantage that was seen at the time is that it allows you to make your design once and just target various technologies. So it ensures possibility, because even if you have open PDK, completely free PDK, when you change of PDK, of target nodes, you still have to redevelop all your standard cells and all your design, especially in digital. So it's costly. With Symbolic, you can hope to not do that. Just develop once and then port to every technology. So next, what we are using currently under Coriolis is a somewhat mixed approach, an hybrid approach, which is developed by Chips for Maker and staff Veragen, which is based on stick diagram. We make stick diagrams of our library, and then we expand them in real shapes. So it's still under NDA, but the source of the library can be automatically expanded to each node. So it eases up the work of migrating from node to node. So Coriolis can work with in three modes: real mode, Symbolic mode, and FlexLib. Now that I have presented the various components, just a small reminder about what making an ASIC is. We have seen a lot of nice picture yet. So an ASIC basically is just a layer, it's just a drawing, a big drawing following very complex rules, but it's a drawing. This is what you send to the foundry, and the foundry sends you back the physical object, the chip. Basically, it's we do that under a V cycle. So on the left part, what you do is break things apart with a logical synthesizer, typically IOSIS. So you start from your RTL description, register transfer logic. So it breaks out everything in terms of little standard cells. Each standard cell having its layout counterpart. Once you have broken them down to the standard cell level, then you rebuild them and you rebuild your full layout with two standard steps, which are the placement, then the routing. The placement, make the placement of all those tiny layouts without overlap, and the routing, draw the wires that connect them. It's quite simple at first glance. So, how do we assemble our design flow? I will detail the Coriolis design flow from bottom to top, sorry. So we start at the bottom with the library, which is FlexLib currently. We can use other library, but the one we are using now is FlexLib, which is based on the old Alliance A6lib and NA6lib. So these are our standard cells. Then we use K-layout to adjust them on any or perform some operation. We use Alliance and Coriolis to perform the place and route and some validation steps. Alliance can still be used to make validation. Coriolis is the replacement for the PNR. So then we leave the physical synthesis stage to enter the logical synthesis stage, which is done by IOSIS. I think almost all free tool is using IOSIS, thanks to Claire Wolf, very amazing tool. On top of that, we have GHDL, for example, and NMIGen. NMIGen is hardware description language like HDL, but you can use any hardware description language. As long as you produce VHDL or Verilog, your Coriolis can use it. So I did put that because that was what we were using currently, but there is no obstacle using anything else. GHDL, of course, is in VHDL and is used to resimulate. And finally, we have on the top level the LibroSoc. LibroSoc is, in fact, the level of people doing ASICs. So they are using all the stack. I am being too long. So here is the NA6lib library. I will go fast. So it just.
No, I just was moving you out of the way because I couldn't see a part of your slide. Sorry to confuse you.
Sorry. So just a quick flip backward to the NA6lib library. So it contains 89 cells, logic gate, day flip-flop, and so on. It has been validated because we have made design with it. So it has been sent to the foundry, so we know it works. So it's also used as the topological base for FlexLib, as I said. My staff there again. Now, I will talk about algorithms. Algorithms that are implemented in Coriolis and in any EDA tools have a big problem, is that you cannot optimize one without optimizing the other. So the naive schematic is that one. You have separate steps, well defined, and you run them in a row. So you start from this is not an algorithm, this is just input data, your standard cell library. Then you place them, then you global route them, and then you detail route them. But that does not work like that. I mean, already each one of these algorithms is NP complete. No, the problem, sorry, not the algorithm, but the problem is NP complete. So we need quite powerful algorithm to solve them. But the problem is worse than that. For example, we have interaction that is there. Fundamentally, we are breaking apart a problem which is a wall. To manage it, we need to break it into separate steps, but in fact, those steps are interlinked. So typically, we can have, if I talk about if I envision the saturation problem, that is the fact that you have enough space to route your design. Sometimes you perform a placement, you perform a global routing, and you perform a detailed route. And the detailed router said, no, I cannot complete because you have some areas that are overcrowded, that are saturated. So what you can do at that point, you have to send back information to the earlier stage. So now the first idea was just to make a big loop like that. Okay, I extract information from the detailed router and send back to the placer, and we go again. The problem is that by doing that, you may create other denser area on other places. So what we want to do is something more closer to each step. So the idea is that the detailed router will feed information to the global router, which then may feed information to the placer. And to perform an advanced EDA tool, you must interlink all the stage, all the algorithm. And this is at the heart of Coriolis. That is, we have all the information interlinked. So this has deep implication about how you build your software. Here is a very schematic figure about how Coriolis is organized. We have a central database, Hurricane, onto which all the tools are binded, and they communicate both through the database and also directly between them. Here, in the lower part, I did present how the G cell is organized. G cell is one brick of the global routing. The G cell is used also in the detailed router. It's used also in the global router through the vertex. And what we do is decoration. What is very important is that you don't rewrite different data structure doing the same thing. What we do is systematically decorate. We decorate the Hurricane database. The global router decorate Hurricane, and the detailed router, which should be here, the detailed router also decorate the global router. So we have all very tightly mixed. We have also an important thing, which is it's completely in Python. In fact, Coriolis is just a set of library in C++ with Python interface, and all the glue is done by Python. Even the binary, there is no binary in Coriolis, there is just Python scripts. And everything is accessible through Python. So finally, one other nice feature of Coriolis is that we also developed a new approach to make analog design. We have the capacity in Coriolis not only to make digital design, but also to make analog designs. So what you see here is the G-cell matrix. So on the digital part, the G-cell matrix is perfectly regular. But under the analog area, it's organized as a slicing tree. What you see is a slicing tree. The matrix, the G-cell matrix, is piloted, is driven by a slicing tree into which you can do your experiment. And the interesting thing is that the global router is just the same for the analog part and for the digital part. We route with the same router, which is able to handle analog design. I mean, analog constraint. For example, you can request the global router to perform symmetric routing. You have two wires, two nets that you want to be routed symmetrically. You can do that with Coriolis. And the detailed route, of course, follow the same things. It can route symmetrically. So I will go quickly over that. It's the the schematic of the flow of the design when you want to make a symbolic layout. It's the schematic, and you have a simple rule which is make layout. In fact, the flow, the tools of the flow are glued together by makefiles. That is, I make rules, a lot of rules, and we can just, in the end, make layout. Same goes for GDS, for the real flow. So if you want a GDS instead of symbolic layout. And finally, the logical synthesis. I will go fast because I lack time. We can also perform some validation through alliance. We can perform a LVS and DRC, but DRC on symbolic layout only. We are looking to expanding toward real DRC. So in the end, what we did was that is the LibreSoc chip, the LibreSoc full chip. It's about 120 kilogates. It implements a Power 9 instruction set. You can see here on the top left part of the chip the RAMs. They are 4 kilobytes RAMs, 4 kilobytes RAM, sorry. On the top right, you see a little PLL. It's teeny one, but it's a PLL, and then all the rest. So the standard cell part is about 120 kilogates. The whole things contain about 1.3 million transistors. It's an approximate, of which 800 are in the SRAM, and the rest is in the standard cells. The chip itself is about 5 by 5 millimeters. And just to give you an idea, it routes about, I need to look at my figures. So I think it's below the hour. You can have that layout in less than 1 hour on my laptop, which is a Core i7. And so I think the placement lasts 39 minutes. Okay, I have the numbers. Okay, 32 minutes, sorry. 32 minutes for the placement, 5 minutes for the global routing, and 6 minutes for the detailed routing. So it takes about three quarters of an hour for that chip. So what is working in Coriolis now? We use H3. We have implemented the feature of H3. We have high fan-out net synthesis, and we have antenna effect protection. What we are working toward is, of course, support the Caravelle harness to allow people using directly our tools and submit them to eFabless. And then add timing closure to support lower node, because what prevents us to go lower, below 130, is that we don't have a good timing support. So this is the long-term priority. So now we can have a little demo about what we can do. So I will go fast. This is the start. This is an example which contains the Verilog file. I don't generate the Verilog. It was supplied to me. And we have basically the MK link, which is a link toward the makefile rules, and a top-level makefile, and a dodesign.py, which is the description of the design. If we look at dodesign.py, it's a simple Python script which basically defines. This is more clean. So basically, it defines where your I/O pins are, plus some configuration concerning the place and route. So I don't have time to go into them, but you can see that the file is quite short, and it can be templated. It doesn't vary very much between them. So first step is to perform the synthesis. So make VST. We just call IOSIS. People knowing IOSIS will recognize its output. So we just take a little bit of time to perform that. So it will take about 5 minutes, not the whole bench, not just IOSIS. I have been a little bit too long. I'm very sorry. Okay, maybe I should have done it before, because I'm a bit slower because it's on my laptop, so it's running really live, and maybe the streaming is slowing it down a bit. I have the impression that it was faster last time I ran it.
When you gave me the little demo before, I think you used a much smaller design because it just popped up straight away with the
yes,
the interactive stuff.
Maybe do you want me to go to something faster?
Well, actually, that's a good question, because we had this is something that I'd like to ask the audience. So for people listening on wherever you're listening, just let me know in the comments. We've got we're going to be running 10 minutes over time if we stop this presentation now and continue as we wanted, because we've got a 10-minute presentation from Luke about LibreSoc, and then a 20-minute talk from John McMaster about the physical side of MPW1. He's got some great die shots of MPW1, so you don't want to miss that.
So I will make shorter.
I think Jean-Paul, you should run that much smaller demo that we can get a result out of quickly.
To the smaller one once I can kill this one.
In the comments, could people let me know whether they would like Luke to do a short summary of LibreSoc and check the YouTube video out later, or we run 10 minutes overdue and we'll finish at 10 past the hour.
Okay, so I switch it to a smaller one. So you see, now we have Yossis, and then we can perform the place and route. So I will just launch the script, the do design script. You can type it correctly. So this is the clock tree. First step is to build the clock tree. There is 2 wires because we use a clock tree and also an edge tree for the reset signal. So this is why you have 2 wires. So there are 2 clock trees. So then we perform the placement. And what you see here is the SimPL algorithm at work. So this is the lower bound placement which is displayed. And you see it will stop when it reaches 10%. So just a word about the GUI of Coriolis. The GUI of Coriolis is intended as debugging purpose, mainly. It's not an editor, even if you can do it. It's intended as especially for debugging. So now you have the placement done. So we are doing here. We are just before the global routing. So what we can do, for example, is highlight all those lines are in fact the nets. So if I synchronize the net list and find a nice routing pad, nice one. Okay, find, for example, I don't know. So N499 to make it alone. Selection. Here is a net. I just selected it. So now I make just a zoom on it. So first, it's only fly line, because you see maybe the little blue dot at the end. They are the connectors. So then we can perform the global routing. Here, the global routing has been done. And you see the trunk of the net, and you see the little cyan line that remains, because this is the end to be done. This is the end of the work that has to be done by the detailed router. So you can also display fun things like G cells. Okay, it's not very contrasted because this design is not very dense. But what you have there is the density map. You can also print the edges. Oops. Here you have the edges. Maybe it's a little bit. So you know here that you have four wires going through the edge of the standard cells. Not the G cell, sorry. So we will refocus on it. No. And finally, we can perform the detailed routing. Here is done. Now the detailed routing has been done, and the design is complete. So it's very fast. Yeah, at least I find it quite fast. So you have also the ability to inspect your design. If I can, where is it? The inspector was gone. So we have an inspector also. You can inspect the design, and here you have the ability to see the C++ database. The C++ database is completely inspectable, and you can, for example, look into the net map and see all the nets and go into a net, into its components, and so on. So this tool is very useful to debug, especially done for debugging and debugging your live programs. That is, I can stop the placer at any time I want. I can stop the global router also at any point I want and see its state at any moment. So it is. I have to get back my window. And maybe one last demonstration, which is here, about the capabilities for analog design. Next is GT. Okay, CGT directly. Okay, so now here we are. We have an analog design, which is, I think, a part of the entry stage of amplifier OTA. So the interesting thing is that you have an exploration tool here. So the designer has defined a slicing tree for this design. And what we have here is all the possibility for the slicing tree, and you can interactively choose one. For example, a very bad one. Here in green is the Pareto front. So if I choose this one, so it's placed en route and global routed, but we can finish by detailed routing. Step by step. Detailed route. And now we are detailed routed. You can look at nets, net list. Okay, you see all the nets. I don't remember which ones are symmetric with the others, but maybe you can see it. But some of them are symmetric, not all of them. For example, this one is quite symmetric. So I'm sorry to have been so long, but I have finished.
No need to apologise. We've got a very understanding audience who said that they prefer to run over so that we could get the most out of these very interesting talks. Yeah, people are saying, great tool, the real-time view is amazing, love the visuals, run over please, just make sure we have the video on demand later. So it will be obviously on the channel later. So thanks very much, Jean-Paul, it was really good. I definitely learned a lot. And I also, yeah, love the kind of the interactivity, the inspectability of the design. So looking forward to learning more about Coriolis 2 later.